Hi everyone, this is Manmeet Singh, MS17164 of Physics Department, and today I'm going to present on the topic quantum key distribution by using BB84 protocol based on published paper Quantum Cryptography Public Key Distribution and Coin Tossing written by Charles H. Bennett and Gilles Brissel. Quantum key distribution is a secure communication method which implements a cryptographic protocol involving components of quantum mechanics. It enables two parties to produce a shared random secret key known only to them, which can be used to encrypt and decrypt messages later. The importance of studying this subject is that when two users communicate and we want to detect a third party presence trying to interfere and as you know leak they want to get the message they want to leak the message between the two and get the information for themselves, so it helps us to avoid that because in this using these quantum mechanics aspects we can detect that third party presence if a signal got leaked. And the fundamental principle behind its working is that quantum indeterminacy involved in measuring of aspects of a quantum system. As we know that when a quantum measurement is made, the state of the system will usually generally it's changes or is disturbed. The only main drawback is that of this method is that everything can't be just communicated using quantum channels. There is a need of information to be flowed, information to be sent through classical channels also. BB84 is basically a quantum key distribution scheme developed as you know by Bennett and Brissett in 1984, and was the very first quantum protocol, quantum cryptographic protocol. And it relies on the quantum property that information gain is only possible at the expense of disturbing the signal if the two states one is trying to distinguish are not orthogonal, and an authenticated public classical channel is also needed, and it is usually explained as a method of securely communicating a private key from one party to another for use in one-time pad encryption. Now to get into detail, let's see. First, we will decide that encode, or you can say that four single qubit states 0, 1, plus, minus in these four directions as we will assign them, and these are 0, 1, these are the cats of eigencats of the SZ operator, and these are of SX operator as we know from the spin half Hilbert space, or you can say these are directions of Bloch sphere we know from where we already know. And uh, this up down direction will be represented by this thing, and uh, left will be right will be represented by this one, and blue and red will represent the classical inputs in both cases, which will be 0 and 1. Now, if we want to see how measurement is performed, uh, as we know, if the measurement basis and this input state align, then outcome will be exactly the same as the input with no change, or we can say that we can completely predict the outcome with probability 100%. And as is shown in this case clearly, and this is for sz1 and this is for sx1. But if the random if we the input we don't know about and the basis we chose to measure were orthogonal, then the outcome will be either the firstly that the input qubit will get totally changed. It will be either up or down, but the encoded classical information behind will be either blue with probability 50% or the red. Now let's see BB84 protocol, how it works. Here Alice is the sender and Bob will be the receiver. And let's see, Alice draws a random sequence of blues and reds, and after that she chooses a random sequence of directions. In our case, these will be the different SZ or SX bases in which she decides to measure, and using these two sequences she can encode the single qubits, uh, see and get the sequence of that, and Alice will share this sequence or send this to Bob. After receiving these sequence of qubits, Bob will draw his own random set of bases and measure these qubit inputs according to that set of bases. And as we know from the measurement slide that if the input qubit and the measurement that randomly he chose and direction got aligned, then input qubit and output qubit will be totally same. Obviously, the classical information gets will also be in the same red one in this case. But if the basis chosen was orthogonal one, then the output qubit will definitely change, but the encoded classical information behind will either be the same as the blue one in this case with 50% probability, or it will be different with 50% probability red one, as it's written here. And uh, uh, this signals after getting this drawing out these signals, what will happen is that both of them a quantum communication channel is over, quantum channel work is over here. Now what is the second step is the post processing step, which requires us the sharing information through classical channel. And in this step, both Alice and Bob will release their sequences of measurement bases which they chose in the public. And both of those will tally from the sequences and cancel out those measurement bases which they chose were different. Now, what will be left will be after cancelling out will be the only list of those bases which will were same, or basically the same input which Alice chose and same output the Bob got, and or encoded classical information will be same, or basically same input key and same output key. Alice and Bob are able to share successfully. But what is the advantage of doing all this thing is that if a eavesdropper third person, say Eve, tries to interfere in the between the um and receives the signal sent quantum signal sent by the Alice, what will happen is that he will be able he will totally change the input sequence into a different output sequence, as we know from the aspect of measurement of quantum mechanics and discussed earlier. And the later Bob which we will get sequence, its output will be again totally changed. So the output Alice Eve receives will have no significance at all, even if he gets the basis list same shared by these two. And as the after crossing the input and output key, which both of them will receive, will be known only to them. And even if the Eve scheme matches some to some extent, then what will happen is basically that Bob the string of the key will get shortened out under matching and to quite a shortened out. And if Bob and Alice will can set a number, and that if a key shortens then this number, and they can basically guess that some third party has interfered and they need to resend the message. And this concludes the presentation, and we have successfully shown that a secret key can be shared through this method without need to communicate secretly beforehand, and it can be used as a one-time pad scheme for sending messages directly. Thank you and have a nice